The next book is Norman Johnson, Geometries and Transformations. So it is all about geometry from the Klein point of view. So it has homogeneous spaces, linear geometries, circular geometries, real collineation groups. It has equiareal collineation, real isometry groups, complex spaces, complex collineation groups, circularities and concatenations, unitary isometry groups, finite symmetry groups, Euclidean symmetry groups, hyperbolic Coxeter groups, modular transformations, quaternionic modular groups. So this, yeah, as it says, this book was basically a misbuy. I should never have bought this book. I was too excited to learn this theory, but it's not a good book at all. Really didn't like this book at all. If anybody wants this book, you can buy it from me. Then we have Vargas, Differential Geometry for Physicists and Mathematicians, Moving Frames in Differential Forms, from Euclid past Riemann. So here we have, it has orientations, differential forms, vector spaces and tensor products, exterior differentiation, affine Klein geometry, Euclidean Klein geometry, generalized geometry made simple, affine connections, Euclidean connections, Riemannian spaces and pseudospaces, extensions of Cartan, understand the past to imagine the future, a book of farewells, and then appendices on geometry of curves and surfaces, and some biographies of Cartan and Grassmann. So yeah, like the book says, this is a very nicely written book about geometry in a very nice style. I don't really think it's that well written though, but yeah, I was very into this kind of stuff back in the day. Next we have TAP, Differential Geometry of Curves and Surfaces. So there's curves, there's additional Toppleton curves, there's surfaces, there's a curvature of a surface, there's geodesics, the Gauss-Bonnet theorem. So this basically is a run-of-the-mill curves and surfaces book. But I mean, I guess there are very nice illustrations though. It's very neatly structured. It's kind of a replacement for DoCarmo, and I think it's quite on the same level as DoCarmo. And quite as good as DoCarmo too. Definitely a book I would recommend people to do. I think it's a work of art really. The author really put time into making a very neat book, and really showing it's very nice. Next we have Burke, Space-Time, Geometry and Cosmology. So if you don't know Burke is somebody who's very interested in this kind of stuff, in kind of geometry and this kind of relativity and how it relates with geometry. So here we see a special relativity, we have geometry, we have gravitation, and you have cosmology. So yeah, it's gravitational book. I like this book. It's neat. I guess more is better than this one, but this is definitely not a bad book at all. Here we come to Geometric Representation Theory by Krantz and Parkes, which is about measure theory but done geometrically. So it starts with basics, with measure theory, Carathéodoris construction and lower dimensional measures. Then we have invariant measures and the construction of the Hahn measure, covering theorem and the differentiation of integrals, analytic tool, the area formula, the co-area formula, and the Poincaré inequalities, the calculus of differential forms and Stokes theorem, introduction to currents, currents and the calculus of variations, regularity of a mass minimizing current. So this is, a book on measure theory basically, but more advanced than you would see in undergrad. It has stuff like fractals. It has stuff on Hahn measure, on groups. This is like the general divergence theorem. I think because it does this kind of thing that I bought the book, because it's very rare to find a book doing these kind of general theorems. Didn't read the book completely, but it does have some good stuff. Here we see one of the most famous general relativity books, Space, Time and Geometry by Sean Carroll. So yeah, it's about general relativity. It covers special relativity and space-time, manifolds, curvature, gravitation, the Schwarzschild solution, more general black holes, perturbation theory and gravitational radiation, cosmology, quantum field theory in pure space-time. I think I bought the book quite a while ago, maybe a decade ago, because I was interested in general relativity because it's quite mathematical. But I never quite finished the book because I got stuck because I didn't know too much physics back then, and I was very confused with some things he was doing. So I never read the book completely. I heard there's very good comments about the book though, so check it out. Here we see one of Spivak's comprehensive differential geometry books. So it is these 5 volumes of differential geometry. So this is has hypersurfaces, elements of the theory of surfaces, compendium of surfaces, curves on surfaces, complete surfaces of constant curvature, and the Gauss-Bonnet theorem. So Spivak is a weird writer. I think he writes not that good. He always has very difficult exercises, very tough exercises, but I don't think I would recommend this book beyond its very nice drawings and very nice art. Here we see 3 volumes of Methods of Algebraic Geometry by Hodge and Pideaux. So it is a 3-volume book. So it covers rings and fields, linear algebra and determinants, algebraic dependence, algebraic equations. In book 2, this projective space, Grassmann coordinates, collineation, correlations. So I think I bought this book back when I was doing my PhD because I wanted some more classical algebraic geometry to shine some light on why we do schemes to begin with. Safe to say that this book did not help with that. Yeah, his book 3 is birational geometry. So yeah, if you're interested in the classical view, this is the book that you this is basically the best view on classical algebraic geometry if you don't want to do the modern point of view of schemes and varieties. Here we see Analytic Projective Geometry by Casas Ayavero. So it has projective spaces, projective coordinates, affine geometry, duality, projective transformations, quadric hypersurfaces, classification and property of quadrics, further properties of quadrics, projective space of quadrics, metric geometry of quadrics, 3 projective classifications, perspectives for artists, models of non-Euclidean geometry. So this is an analytic point of view, not a synthetic point of view of projective geometry. Very comprehensive view on the subject. Again, very classically, this is not the kind of projective geometry that's done these days anymore. But yeah, it's still a book I think that's worth reading. Here we see Hartshorn's projective geometry book. Very thin little book. And it has Desargues theorem, digression of groups and automorphisms, elementary synthetic projective geometry, Pappus's axiom, projective planes over division rings, introduction of coordinates in a projective plane. So very old book. It doesn't even have LaTeX. So it's Hartshorn, of course. It's quite a reputation. But the reputation is not only that he's very hard, but also that his work is very beautiful. Then here we have Measure, Topology, and Fractal Geometry, which is a book on fractals. Is there no table of contents? Apparently, oh, here it is. Fractal examples, metric topology, topological dimension, self-similarity, measured theory, fractal dimension, additional topics. So I wanted to read more about fractals, but I did not like this book too much. I think maybe it was too hard for me at that time because I bought it when I was still an undergrad. I did my undergrad thesis about this topic actually. Maybe I would appreciate it more now. But yeah. Here we have Lewis, Algebraic Geometry and Arithmetic Curves. This was my Bible when I was doing my PhD in algebraic geometry. It has commutative algebra, general properties of schemes, morphisms and base chains, some local properties, coherent sheaves and Čech cohomology, sheaves of differentials, divides and applications to curves, birational geometry of surfaces, regular surfaces, reduction of algebraic curves. So this says this is much like Hartshorne, but I think much more complete and much more readable. Like the proofs make a lot more sense. I read a lot of this book and I really liked what I read in this book. It is focused on number theory though, but you don't really notice any number theory in this book if you read it.